Welcome, everybody. I'm Francesca Moglia from the European Photonics Industry Consortium, EPIC, and I'm really pleased and excited today to be here with you to introduce you and moderate the first LAMpAS webinar, where LAMpAS is one of our EU-funded, so European Commission-funded projects. And if you see behind me, you can see a bit of the of our roll-up describing it. So we will have today two speakers from the consortium of LAMpAS talking about surface functionalization through microstructuring. I would like to introduce you to our first speaker of the day. And so our speaker is Andrés Lasagni, that is coming from the University of Technological University of Dresden. And he will introduce our first topic, and that is about the introduction of direct laser interference and patterning. And he will talk a bit about the application, but also the technology development that is behind it. I would just like to remind you that you can ask questions always during the talks, but they will be picked up only at the end of a single talk. So, and then if some questions are not answered, they will be possibly answered also after the webinar. So don't worry, if you're really interested, we will collect all the questions and this will be answered then afterwards. So if Andrés is ready, I can pass you the floor and the audience, and they are both yours.
Okay, thank you very much. I hope you can hear me well. Welcome to our meeting regarding the LAMpAS project that has received funding from the European Union Horizon 2020 Research and Innovation Program. I would like to introduce you today a technology that we have been developing in the last 15 years, which is called direct laser interference patterning. And our main objective is to use this technology for functionalizing surfaces. First, just let me say where are we coming from. So we are placed in Dresden, in the east part of Germany, in the south of Berlin, very close also to the Czech Republic. And together with the Fraunhofer Association, as well as the Technical University of Dresden, we create the Center for Advanced Microphotonics camp, where we are developing regarding functionalization of surfaces, but we don't stop there, and we also work together to bring this new knowledge to the new industry by developing optical systems, machines, and technology development, mainly to bring these ideas to industrial products. I'd like to start the motivation or describe the motivation of the talk with the next slide. So this we can see here several examples from natural examples. So what we are doing is not new. We are just looking what nature has been doing the last millions of years of evolution. And just to describe some examples, in the first one on the top part of the slide, you can see a blue butterfly, which is in Brazil as well as in the north of Argentina. And this butterfly has a blue coloration, but there is any kind of pigment on its surface. The color that we observe is the result of a photonic structure which is written, let's say, in the wing of the butterfly. So we have a periodic variation of the surface topography, and because of these special characteristics, this butterfly is only reflecting the blue light. Then we have other insects. We have a springtail, which has a very complex geometry, which is about 600 nanometer in size. And because of this complex topography, bacteria cannot adhere. So this insect has antibacterial properties. In addition, there is a bigger structure, which is providing mechanical stability to this surface, which is also very, very important. The last example, there we can observe a snake. This snake has also a quite complex surface topography. And the result of this topography is that the snakes, or also as well other reptiles like the sunfish, they have a low friction coefficient on the surface, and therefore they can move very fast in the sand. So very interesting example. So what we learn is that by producing such kind of scale features, we can, with complex topographies, we can achieve a lot of different surface functions. And this is what we want to do with lasers. So as you can observe in this slide, there are a lot of scientists that in the last 20 years have been publishing about how to control surface properties by controlling the surface topography. Just to mention some examples, in the field of tribology, scientists have found that by producing structures with feature sizes in the micrometer, and in some cases even in the sub-millimeter range, it's possible to control friction and wear. Regarding biointerface topics, also scientists have shown that it's possible to control or reduce bacteria adhesion as in the springtail, but also to improve the cell attachment to different surfaces, like, for instance, the implant materials, so that we have a better biocompatibility. And this for a lot of different kind of properties. So now we come to the point, which is the first challenge. As we have seen, we need small feature sizes, but to bring something into industrial production simultaneously, we have to be fast enough. Therefore, we need to look which technologies are available for that. And what we can observe in the diagram, if we think on one-step fabrication methods, what we see in general is that if we want to produce small feature sizes or structures with small feature sizes, normally we have low fabrication speeds. There are other methods that provide better resolution, but they are based on lithographic processes, which means you always need a photoresist. You also need to make some irradiation, some development of the material, and so on, which is can be very complex, especially when thinking on normal products. And our target in LAMPAS, as well as our target at the camp center, is trying to get both things simultaneously, which means high throughput, faster than 1 square meter per minute, and simultaneously to have a high resolution, which means small feature sizes. Now I will tell you how are we going to do that. Now we come to the second challenge. We want to do this with laser systems. And for being fast, it is clear we need high laser power. And the laser systems that are available today and that will be developed in the next years, we have two scenarios. The first scenario is lasers that provide low pulse energy at very high repetition rates. So let's think that we have 1 million or even much more, 1,000 millions of pulses coming in 1 second on the material surface. This is very nice because clearly we can be very fast, but we have a problem. The first, that we need to move these laser beams very, very fast. In some cases, we're talking about kilometers per second, which is really hard to obtain. And then because of the characteristic of high power laser and these small feature sizes, in this case, we have significant heat accumulation. So this is a problem that we need to avoid and that we also need to solve in the LAMPAS project. The second scenario is to go to high pulse energies. So when you go to high pulse energies, then you do not need so fast repetition rate, so we can work with some million of pulses per second. But because we bring this energy in relatively large spots, we have the problem of the resolution. And if you remember about the natural examples, we need to produce structures in the micrometer and even the sub-micrometer range. So can we get both high resolution and throughput? That's the big question. And the answer is yes, of course, what we want to do in LAMPAS. We're going to combine two technologies. The first one, which is called direct laser interference patterning, that I will show you I will show you later that by overlapping different laser beams at the surface, we can create periodic structures with small feature sizes. And simultaneously, we are going to use these interference patterns in combination with high-speed beam deflection systems like polygon scanners. That brings us to the third scenario, which is now, because we are making within this spot the small feature sizes that we are going to translate into the surface of the material. So we can use, let's say, relative moderate 100 meters per second, and we get a high resolution to the interference pattern. And this is what we are going to do in LAMPAS. Let me tell you a little more into detail what is direct laser interference patterning. So differently to conventional direct laser writing, direct laser writing, what you are doing, you are moving your laser beam on the surface of the material. It's like writing with a pencil, but you are using laser light with high intensity so that you can remove material for the structuring process. So, but here what we do, again, we put 2, 3 or more laser beams at the same position. And when you do that, we have a so-called interference pattern. So that means we create a periodic variation of the laser intensity. This is like having a stamp of light. And with this stamp of light, you bring into your material and you can perfectly transfer the shape of this interference pattern on your material. It means that you are not writing each line simultaneously, so you are doing the whole structure in one process. So you get all lines simultaneously with one laser pulse, or you get all these dot-like structures when you do 3 beams in one irradiation step. The other thing that you can a little look into the equations that are there is that by changing the angle between the laser beams, we can perfectly control the size of the features, which is given in this case by the letter P. That means if you look in the equation, we can get structures which are half of the size of the laser wavelengths. That means even in sub-micrometer range. So what can you do with interference patterning? There are many things that you can do. Firstly, you can treat different materials. We can treat polymers, metals, ceramics, and coatings. As I mentioned before, if we just change the angle between the laser beams, we have the capability of perfectly controlling the spatial period. That means the size of the periodic structures from 150 nanometers, for example, to 20-30 micrometers. Depending on the configurations that we use, we can already reach with some pulse laser system high throughputs. So we are talking about 1 square meter per minute, which is very relevant, again, when thinking on the industrialization of a technology. Time is money and time is speed. So if you're faster, you need not so much time. If you don't need so much time, you are cheap. That's the idea of the thing behind LAMPAS also. And we can get different improvement on surface functions like reducing friction, creating antibacterial properties, improving the biocompatibility of implants, and made decoration, product protection, as well as to control other properties like electrical resistance. Now I would like to show you some examples of large areas that we have already processed. Here what you observe are so-called slips or cylinders that are used for roll-to-roll processing so that we can even be a little faster. The structures that are shown in this example are very complex. That means we are changing from position to position the characteristic of the geometry of the patterns. Therefore, you observe different colors, let's say, on the surface of the materials. And this is a fully automatically process because the development of different algorithms as well as software in combination with the optical heads. And you can see here other areas that have been processed steels, 300 by 300 millimeter. Then we have some stamps. There was a cooperation with company Uch for making product protection elements for license plates, as well as some decorative elements like this rainbow. This rainbow that you observe there, this is on a stainless steel surface. So it's not just a draw. This is a structure that was created with this technology on stainless steel. So how do these structures look like? And we can observe some examples on metals on this slide. So we can make typical line-like geometries or pillar-like geometries. I hope that you can see very well the homogeneity and the aspect ratio of these structures. But there are also other things going on that are related with the kind of interaction of the laser light and the materials. Not going to go into detail, but we have some self-organization processes. And these self-organization processes are responsible of creating additionally the so-called LIPs, laser-induced periodic surface structures. That means that at the end, on the surface of these metallic examples, we have three different length scales. We have the structures related to the interference pattern. In the example are about 5 micrometer in size. And then we have two kinds of LIPs, the structures, which have some sizes of 800 nanometers and 150 nanometers. And if you remember, again, the natural example where we have a combination of several length scales, this is really good news because we can further improve the characteristics, the functions of different surfaces. So at the end, we have a kind of stamp, let's say, of light with our interference pattern. Here you observe when we overlap 4 laser beams, the dot-like distribution that we obtain. And then we have to put this energy on the surface of our material. And by developing such a strategy, by controlling the distances between the individual spots, we can also create very complex geometries. Here in the image, we have some beautiful structures with very complex geometries that were created on polymer materials. This is exactly the same machine working only with 2 laser beams making the interference pattern. But if we play in the way that we distribute this energy on the surface, we can also create, as I said before, complex geometries with advanced surface functions. Okay, what about applications? I'm going to show only 2 applications of the lot of them. Some applications that are really visible effects. And the first one is related to decorative elements. For that, you just have to think maybe on the surface of a CD. Remember, for the generation that uses CDs, maybe the young people, they don't know anymore what is that. But in a CD, normally when you look at it, you will see a very typical rainbow coloration. So you have the composition of the white light creating a diffraction effect, and therefore you are seeing all this kind of coloration. So when we make a perfect periodic structure, we have exactly the same effect. So with the machines, with the technology that we develop, if you look on the image with this nice coloration, this is stainless steel, we can, for a position, perfectly decide about what color we would like to see. For example, red, orange, green, and blue. But because of the structure that is perfectly periodic, we are observing different colors depending on the position. So there are some equations there. We don't have to go into detail, but just because the observation or the angle of observation, depending on the position of the sample changes, the person sitting there or watching there is looking at different color depending on the position. So our idea was now, just to show some examples that are still very interesting. some of these kind of decorative elements you see in notes, in money, you know. So there are this kind of nice holographic structures. Then we decided to change a little the strategy, and because we can change everything during the structuring process, we decided to make periodic structure but with variable spatial period. That means now that depending on the position, we have a different spatial period, and if we respect very well the equations, let's say, we can, independently on the position, make a structure where the observer will also see the same color. And this is the result that you see very well on this metallic part with red, orange, green, blue colors, which are very, very well defined. So if we understand how to do this, then of course we can start to make some motifs, some images, some figures, like very famous Bart Simpson. So you can observe that independently on the position, we get different colorations without the rainbow color. Other example that we are working on that right now is regarding to self-cleaning properties. I imagine you can hear a lot about super hydrophobic surfaces. So super hydrophobic is a characteristic of a surface that water cannot adhere. So if you put a droplet of water, like in the image, you can observe there aluminum sample, aluminum material. We are putting a water of droplet. You can see it gets a spherical shape because it cannot wet the surface. But now, because of that, the water droplet will start to move, will start to roll on the surface. And now if we look when that happens, so you can see on where the arrow is showing the dirt starts to adhere on the water droplet. And when this droplet further moves, has the ability to remove the dirt, has the ability to clean the surface. That means this surface is not only super hydrophobic, but also has the properties of self-cleaning. You know this example very well, probably from the natural lotus leaf that exactly has the same property. So now let's talk a little some achievements regarding the technology development. Today we have different configurations for doing this. We have configurations which is designed mainly for nanosecond laser pulses. And what we are doing, we are shaping the beams. We are getting beams that are very elongated, like 1 centimeter in one direction and 180 micrometers in the perpendicular direction. Inside of these elongated beams, remember we are putting 2 of the beams together. We get the interference pattern, and then when we move our surface, our material at the speed of 1 meter per second, for example, we are like doing laser writing with millions of very tiny spots simultaneously. And therefore we can achieve in this way really high throughputs. Other possibilities of LAMPAS is to combine interference patterning with scanners. So here we're talking about scanners which have speeds of 10, in the best case, about 10 meters per second. And you can see in the image, this is a structuring of, again, stainless steel with a green laser system with only 30 watts of laser power. And we can already achieve impressive throughput of 125 centimeters squares per minute. Remember again, only with 13 watts of laser, we want 1,000 of watts. The amazing throughputs we will be capable at the end of the project. Also design some systems that are available, which combines such kind of optics. We are talking again the optics based on scanner technology, and by doing that we can also work with different laser wavelengths and integrate different laser sources for make such kind of structuring process at high throughput. So what's next? And this is what I would like to give you as message to take home. And of course is our LAMPAS project. So I think you already have the ability to understand how interesting it is to get these interference patterns, again, because we can provide high resolution, we can provide high advanced surface functions. And we are going to combine in the LAMPAS project the interference technology with polygon scanners with high-speed beam deflection systems provided by NextScan technology. Here we also are going to use ultra-fast pulse laser system provided by Prof with a laser power of at least 1 kilowatt, but target is 1.5 kilowatt. And simultaneously, we are also going to integrate inline monitoring systems because we need to assure the quality of what we are producing so that the surface functions are homogeneous also on the whole area that we are working. And one of the process control systems are going to be near infrared cameras provided by NIT. Also, the Technical University of Dresden will develop a Fourier transform-based monitoring system as well as the interference optics. At the end, we are going to integrate all these different modules, the laser, the optical modules for surface structuring, as well as the monitoring systems into a machine, which will be provided by Lasagni. Simultaneously, we are going to develop algorithms to calculate heat accumulation, which is the biggest challenge when working with such kind of by Bosch. And we will, of course, have several target applications that will be described later in the next talk by Andrés from BSH. That means, again, this is the configuration of our LAMPAS project, so the partners in LAMPAS. As you can see again, laser development Trumpf, beam delivery system NST and the Technical University of Dresden, process monitoring NIT, process simulation Bosch, the integration by Lasagni, and then we have different demonstration and validation products that are going to do by BSH and Bosch. EPIC is working in the dissemination of the results, and we are coordinating the project. So I would like to finish with this slide, not to make the talk so long. So again, just go through the objectives of LAMPAS. We are going to develop high power, ultra fast laser sources, 1.5 kilowatts is a lot. And the target is to reach in our final machine throughputs over 1 square, but it's possible 5 or even more. We have a lot of resolution because of the different processes being involved, as you remember, interference structuring, but also we will have the very well-known LIPs. And by designing the strategy, the proper strategy, we would like to minimize the heat accumulation on the materials. Benefits will be the development of a new generation of products with novel functionalities. We will improve the performance of products at least over 20%, which will also permit accelerated product development. And in this way, we are going to strengthen the global position of European manufacturing industry. Okay. Last but not least, I would like to invite you to the LPM conference, Laser Precision Microfabrication Conference, which will be held in Dresden in June 2020. So now the call for abstracts is running, so you can submit your abstract until the end of January. And with this invitation, I would like to finish my presentation. So thank you a lot for being here today.
Thank you, Andrés. Thanks a lot for your talk. So I see that the technology is really interesting because already people ask, can I use it as well? So the questions that now came up were, for example, if you can use this technique on flexible surfaces such as PDMS or, for example, on glass.
Okay, so it's always, the interaction between the laser light and materials is the same as when you are doing conventional, let's say, laser writing. That means for treating a specific material, we need to have the correct laser wavelengths as well as the correct pulse duration. And for answering in concrete both questions, if we can treat PDMS or glass, the answer is yes. We have some work running where we can make even this kind of decorative elements very well on glass materials. You need to go to picosecond sources so that you can try to get so-called multi-photon absorption, and then you can process glass. And for PDMS, it's something similar. Either you go to UV wavelengths where you have some significant absorption by the material, or you can also indirectly do it by using ultra-short pulse laser systems.
Okay, thanks a lot. Then there are some other questions a little bit more on the industry side. So the question is more like, where is really the potential? So do you see that there is a potential for large consumer markets? So do you think that speeding up the process, will it be actually, that is a big challenge as we understood, I guess. Will it be really the point and the challenge to overcome to really reach the market, the large consumer market?
Yeah, for sure. I mean, maybe you know there are some nice videos in YouTube on the internet of super hydrophobic surfaces, and that were done using femtosecond laser radiation. And once I had the chance to ask the person who developed that about the processing time, and he told me that for treating 1 centimeter square, he need like half an hour, 1 hour. So there's no chance of with such low productivities to bring any kind of process of technologies into real products. But now, in some cases, we are capable to make a surface super hydrophobic, and we need for 1 centimeter square much less than 1 second. So, and with LAMPAS, we will be even much faster. So if we can reduce the processing time, then we can really treat large areas at at high throughput, which clearly is correlated with a low increasement of the fabrication cost. So for sure, the improvement of the fabrication throughput will be totally related to the implementation of many of these new ideas, of these new surface functions into real products.
Okay, so I guess we can stay positive. Absolutely. I didn't have any doubt, but now you confirm it also to the audience that they have just to stay tuned, they wait, and we will get it in 2 years. So now there is a bit more technical questions again. So they ask, for example, what is the smallest structure done so far? In size, I assume? The smallest, yeah.
So that will depend on the wavelengths that we are using, the laser wavelength, and the way that we put the beams to overlap. But the smallest features we did in the past using this technology was 150 nanometers. So 150 nanometers for line-like geometries. We did that on a diamond-like coating, for example. But just to get an idea, so you can estimate like half of the wavelengths that you are using. This is like the limit.
Okay, so also with all the tricks of overlapping structures, you don't get lower. Still, the wavelength is the limit, and this is clear also from your slides, so from your formula, the few you showed. Okay, that's I guess a good answer for that. And then another more technical questions, and then maybe we close this session. Otherwise, we don't have time for Ander anymore. So they ask if you could please provide some information on the self-assembly process. So what materials do you use?
Okay, so this self-assembly process, I told you in the presentation, this is called LIPS, laser-induced periodic sulfide structures. They have been observed in the 60s, immediately after the development of the first laser worldwide, a Ruby laser. There was a work in germanium using a continuous wave laser, where this kind of self-organization process were observed. And in general, you observe this kind of process everywhere in all kinds of materials, in particular if you are working with picosecond, femtosecond laser sources. The only thing is that you cannot control this process so well. So you cannot control so well the feature sizes that you obtain. You cannot control so good the geometry, but to answer very concrete the question, in principle, you can get them in every kind of material. You need, of course, to absorb the laser radiation.
Okay, then there are a few questions actually left, but we know that we can answer them afterwards, so that we don't stay too long maybe in talking about your talk. That was, of course, great, but we can take care of the questions later. So I would say now it's time for Ander Villate from BSH, and so you will talk a bit more about the applications. So that's why we really take care that this European funded project talks with the users, because that's a really important thing for us, that we want to have the direct contact with the user. So you will talk mostly about the industrial application of this technology in home appliance sector. So this is one of our strength topic now for end users. So Ander, if you're ready, now the floor and the audience are yours.
Okay, thanks a lot, Francesca, for the introduction. Hopefully you can hear me, see me, and see my slides at the moment. So basically, I will introduce a little bit before we start with the applications. BSH, for the ones who do not know the company. So BSH is a company who is owned 100% by Robert Bosch Group, and we are dedicated to the design and fabrication of home appliances. So we are talking about the entire range of home appliances. Maybe you don't know the name BSH, but probably you will know Bosch or Siemens home appliances, or even if you are living in Spain, you will know Palay or Felmer in Poland. So at the end, we have 13 different brands covering the complete range. So some figures about BSH. So we are #1 producer in Europe. We are more than 60,000 employees worldwide, and we reinvest more or less 4.5% of our revenues in research and development activities. So about the product categories, as mentioned before, we are covering the complete range. We are divided into 5 different product categories. So cooking and baking, refrigerating and freezing, washing and drying, dishwashing, and small home appliances. But we also have an area which is corporate innovation and technology, to which I belong, and we are dedicated, let's say, to more research activities, but always to be developed for the home appliance sector. And more in detail, I am located in corporate innovation in Spain. So here we are a group of more or less 40 people. So among engineers, physicists like myself, or chemists, and we have some competencies in BSH. So some of them are related to the project LAMpAS, like for example, the surface functionalization topics. We have also some groups with developing chemicals for the home appliances. We develop new materials or aesthetic materials. Some people, they are working on hygiene topics. So this would be also related to LAMpAS, you will see later. And we have 3 small groups who are more dedicated to open innovation topics, or digital decoration for home appliances, and of course, advanced manufacturing. So everything which is related to Industry 4.0. So now talking about LAMpAS. So what is BSH's contribution and interest in LAMpAS? Of course, BSH, we will be participating in the specs definition or requirements definition, and also on the definition of the application cases, which I will show you later. So basically, we want to contribute with different use cases so that we can prove the technology, and also we can prove the industrialization of the technologies. We will provide a lot of requirements, but always with focus on the productive environment. So there were some questions before asking, so how far is this technology from the production sites? So this is also a question we want to answer with this project. And our activities will be focused on the objective number 5 of the project, which is processing of a product demonstrator with high performance requirements. So basically, we want to give feedback to the consortium about the performance of all the developments that have been achieved during the project. So basically, the prototype validation. And our interest is clear. So it has been always in our roadmap that it's for us very important to obtain different functionalization of the surfaces, but always talking in inline processes. So talking in the level of the factory, and always in a controlled way. And our expectation and vision for LAMpAS. So again, we want to have a robust industry-oriented prototype, which is able to functionalize surfaces in real time, so that we don't need to do some kind of batches of parts, so that we can functionalize the surfaces in real time during the production. But also we want to increase the value of our products. And that's, for me, maybe the most important thing at the moment, because we have been studying the consumer journey. So for all the different appliances that we produce, we know that there are some pain points that the user complain about, and there are also some functionalities that the consumer is requiring, and we think that with LAMpAS we can cover some of them. So the applications that have been defined in LAMpAS are the anti-finger properties, new decoration finishes, easy to clean properties, and anti-bug properties. So Andrés, before he mentioned that the BOSS group itself is also taking part in the validation of the applications. So Robert Boss will take care about the antibacterial properties, and we, BSH, will be focusing on the first 3 ones. So probably you cannot see anything here in this slide, but basically we started to populate the list of possible use cases for the project. We ended up with 21 different ideas, and we clustered them and we prioritized them to 4 selected use cases. And basically, we were studying not only the appliance or the application we are looking for, but also the differences between the appliances. So of course, we are using different kinds of steel, different kinds of coatings, different kinds of thicknesses, and this will have an impact on the laser parameters that we have to use, but also on the industrialization of the technology in the future. So from these original 21 ideas, we here there are a little bit more clustered in relation to the application. We ended up with 4 use cases that we want to validate during the LAMpAS project. So the first 2 cases are related to easy to clean properties, and the first one is the oven inner cavity and the trays we are putting inside the ovens. So usually the interior part of the ovens, they are quite difficult to clean. So hopefully with the LAMpAS development, we can have an easy to clean application here. In the same way, the dishwasher inner cavity, sometimes we get some dirt or dust there that is not reached by the water during the cleaning cycles. But also at the same time, as Andrés mentioned, when we are able to play with the hydrophobicity or the hydrophilicity of the surface, we are going to be able to develop safe tailored drying processes. Because our disposers, they have a specific drying method in which the droplets attach to the wall, and then we are able to play with these parameters. When we talk about the anti-finger applications, we were looking on massive areas. Our biggest appliance, of course, is a fridge. And today, how we are producing the fridge doors, so there is a stainless steel, and then we are adding a polyethylene layer on top of this. So this is making the anti-finger property today. This is not very nice from a production point of view, but also it's not very nice from a recycling point of view. So with LAMPAS, we are aiming to produce directly the anti-finger property on the stainless steel so that we don't have to use this polyethylene layer anymore. And about the decoration, again, we are aiming to massive areas. And this is, let's say, the topic that is more or less still open. So we are thinking about blackening of the surface, so obtaining dark black colors, but also we are thinking on additional alternatives like Andrés has mentioned before. So obtaining some kind of different colors, for example. So at this stage of the project, we have defined already the requirements. So both from a process point of view, but also from a product point of view, and in addition, the connectivity requirements. With connectivity, we mean everything which has to do with Industry 4.0. So how do we see that the LAMPAS prototype or even the machine in the future should be connected to our production lines? So when we talk about process, there is nothing really new here. We are talking about typical process requirements that we are asking to any machine that we are implementing in the factory. So everything which is related to cycle time. So here you can see, for example, about the cycle time. So here it says that our processes are more or less between 70 and 90 seconds, but in some of our factories, we are going down to 20 seconds. This means that every process we do on the surface has to be done maybe in between 20 and 90 seconds. So that's why we need the development of the LAMPAS. And the rest of the parameters are the typical ones of the machine, so I will not go through them. Now about the product requirements. Please forgive me if I don't give a lot of details here because I cannot disclose all the topics. But basically, we have developed different evaluation techniques for example, for the easy to clean validation. This is a specific method developed by BSH. In the same way, we have developed some methodology to evaluate the anti-finger properties. And finally, our colleagues from Robert Bosch, they have also developed a method, or they are using one method to evaluate the antibacterial properties. Of course, the decoration topics is a little bit more subjective, so this we will need to include our designers and marketing colleagues here to make an evaluation. But let's say this is at this moment the stage of the project. So from BSH side, the use cases are set, the requirements are set. So we are now starting to get the first samples and make the first evaluation of the LAMPAS project. And this was all from my side.
Thank you very much, Ander, for your talk. So we have a bit of a questions about all these applications, how you selected all these cases. So, for example, someone is wondering why you're not interested in antibacterial treatment for some of your appliances. So, will you comment on that?
Yeah, that's a good question. So, basically, as we are two partners who are evaluating the applications, we divided them a little bit. So Robert Bosch, they only had applications related to antibacterial properties. And of course, we are also interested in that. But only to have a little bit broaden the applications, we selected additional ones.
Okay, so it's more like a strategic with the partners to divide this. Okay, I see. Okay, that's, I guess, clear now. And then there's also another question. So I'm looking a bit into the future, and maybe also Andrés can answer this question in the case it's not maybe too technical. So all these properties that are written are separated, but you could actually overlap them in a way that you could have an anti-fingerprint and easy to clean surface. Is this, of course, I expect that the answer is yes for interesting. Is it for you?
Yes, I think yes. Andrés, you know this better than me.
Yes, of course, that is also what we can learn from the natural examples. The surfaces, they do not just have one function. They are, let's say, developed by the evolution to have several kind of simultaneous surface properties. So, for example, something that is hydrophobic, super hydrophobic, very probably it will be also self-cleaning. And something that is also hydrophobic, could be also anti-fingerprint. So there is an interconnection between the different properties, of course.
Very good. Then the last question maybe of the case of today, if at least that we can answer live. You were under a bit, not disclosing much about the validation process, but here there are some questions about if you can give a bit more details. So, for example, how much time? So, at which stage of the project you are able to validate, or how much time you will need for validation? Things like this. If you don't want to say details, I don't ask you too much.
Mm-hmm. Okay. In the case of easy-to-clean validation, I mean, we do not need so much time, and we could even start doing some of this. So we have already done this in the past, but ideally we would like to do this with the development done in LAMpAS, because for us it's very important. It was mentioned before. So when the technology is not ready for industrialization, it's a very nice exercise for us as an industrial company, but we need something that we are sure that we can implement in the factory. So, I mean, evaluation of easy-to-clean properties is easy. It takes five days for us. And for the anti-finger, it's a little bit shorter in time. But of course, there are other requirements that we need to pay attention to. So for example, the corrosion resistance. So every time, of course, we are interacting the laser with the stainless steel, we have a high risk of reducing the passive layer of the stainless steel. So we have also to evaluate the corrosion resistance to aggressive media like acids and so on. So still there are some open points, I would say.
Means that you have to take care in parallel that also this other like a background that is not a background, but let's say is not the focus of the project, but they have to be sustained somehow, and so you have to be all in parallel satisfied. Okay.
Exactly. So we don't have to develop a new property and destroy the original ones.
Yeah, definitely not. Otherwise, it doesn't sound like a successful project. No, but I mean, there are definitely all the expectation for a very fruitful collaboration, I guess. Maybe I ask a personal question to you as the end user. Do you have experience with BSH or with, if you know from Bosch, to work already in such a European funded project directly with producers? So how is it your feeling? Is it important to be there now? Would you like to be later, or even very early in the preparation of the application? Or what is your feeling? What was your experience so far?
Mm-hmm. So I think it's important that the end user is involved in the project since the beginning and before during the preparation of the proposal. And from our experience, I mean, we were leading one European project that was ended 4 years ago, and now we are seeing the results in the factory after 4 years. But I mean, without that project, we will not have the results that we have today. So I would say it's you need time to implement the results, but also for us, it's very important to get some knowledge on board.
Okay, so if we don't have any other further comments from our speakers, I would say, Andrés, is it the case, or should we go on? And
no.
Okay, so I guess
thanks to everybody.
Yeah, thanks to everyone. Yes.
Okay, yes. So then the speakers, thank you all again, dear audience. So as I said, there are a couple of questions still left open, maybe for Ander that can answer them later on. They're a bit more detailed, so they want to know the details, Ander. So maybe privately you can say something more than here online. But I would like really to thank you for being here, for having been here as speakers and as to be here as an audience. I also would like to thank you, the people that will watch this webinar in the next possibly 1 year. So there is a possibility to have this webinar online for such a long time. So hopefully someone will still watch it. We didn't have time today. And also we are open for questions. So I guess our speakers on the www.lampas.eu, you can also find the project itself, and you can contact us for questions on the different work packages. So we are open. Thank you all again for being here, and I wish you a nice winter break. and see you next year, probably live in some events about LAMPAS. Bye-bye.